So I'm going to follow up on what Josh said. Josh gave a high-level overview of our company vision and software-defined data center and what we're enabling. I'm going to go down one level down, and I'm Bhavesh Davda in the office of the CTO at VMware. It's my colleague Aaron Blasius in the product management team for the ESXi hypervisor. So much of this is follow-on from last year's talk. There's a few slides which are repetitions from last year that you'll recall. So last year, and Josh talked about this in his previous presentation as well, is RDMA can benefit in a virtual environment at two layers, both at the hypervisor infrastructure layer for the sort of east-west traffic, and in the guest OS for applications in the north-south traffic. So in the first section of my presentation, I'm going to talk about how RDMA can benefit the hypervisor services. So hypervisor services like live migration, which is vMotion, what we call vMotion. vSAN is what Josh referred to as the clustered direct attached storage solution from VMware. It stands for virtual SAN. Fault tolerance, FT, is the ability to have a hot standby of a virtual machine if the active was to fail. And iSCSI are some of the examples of infrastructure-level hypervisor traffic. Traditionally, they use TCP/IP sockets. VMware in the hypervisor, in the VMkernel, implements a TCP/IP stack. It's derived from FreeBSD. And so these applications living in the kernel address space, but they make direct socket calls, and they use TCP/IP for transport. So TCP/IP appears as connected as a port to the virtual switch, and the virtual switch, whether it's what we used to call a legacy switch or a standard virtual switch or a distributed virtual switch, then has uplinks, and you can have one or more uplinks, and the uplinks can be teamed. Teaming can be for load balancing or HA reasons. So in this picture, we're shown a 10 gig NIC, and you introduce a 40 gig, 10 or 40 gig NIC, which is RoCE capable. And in the green arrows, you see how vMotion traffic flows traditionally over the TCP/IP network, over the 10 gig uplink using TCP/IP. If you introduce an RDMA verbs implementation in the hypervisor in the VMkernel, then you can all of a sudden take advantage of that, make verbs calls into the RDMA stack, and vMotion can then leverage RoCE using the same adapters. Now, in that scenario, you'll notice it's bypassing the TCP/IP stack, it's bypassing the virtual switch, it's going directly to the HCA. So RDMAs are happening directly from the vMotion code in the hypervisor to the HCA. So we presented these early performance results last year, just a reiteration of the benefits of vMotion over RDMA. The total vMotion time in an experiment for a pretty large VM, if I remember correctly, was a 56 gigabyte VM running a workload that we like to use for live migration testing because it's very intensive, demanding from both the CPU point of view and the networking point of view, called SpecJBB. It's a standard spec benchmark. And it's challenging because the characteristics of the workload dirty a lot of pages all the time. So as pages are being dirtied, the state of the virtual machine and the state of the memory is changing all the time, and so you need CPU to do the TCP/IP processing and then the bandwidth on the wire as well. So the total vMotion time reduced from 70 seconds to 45 seconds in our experiments. We could make more effective use of the bandwidth. So we went from on the 40 gig NIC over TCP/IP, we were able to use 30% higher bandwidth from about 11 gigabits per second to 14 gigabits per second. Now this was PCIe Gen 2, and this was the previous generation of a Mellanox ConnectX-2 adapter and a non-optimized TCP/IP stack. So I'm sure we can push higher both on the TCP/IP front and the RoCE front. The most significant savings were on the CPU utilization front because of the benefits of offloading that RDMA offers. On the destination side, we used 92% less CPU for just the live migration parts of it, which means that 92% of the CPU is now available for hosting virtual machines, additional virtual machines or more virtual CPUs than existing virtual machines. Similarly, on the source side, we saw about 84% lower CPU utilization. So in order to make use of RDMA at the hypervisor level for more services, including FT, SAN, vSAN, iSCSI, NFS, and so on, we need an OFED-like RDMA stack in the VM kernel. So in the OFED architecture, it's what's called a mid-layer and provider components. And then we need to add RDMA verb support in the form of an API. Now, these APIs, just like, last year we heard about Microsoft SMB Direct and how they have integrated the RDMA stack or their version of an RDMA stack in Hyper-V or in Windows Server 2012. Similarly, any OS has to, in order to get the most performance out of the RDMA stack, you want to provide native APIs for that OS, so you don't have to go through translation layers or shim layers translating from one data structure to the other or one call format to another and so on. So that's what VMware needs to have is a native RDMA stack that our native applications can make use of. And then you need to create an abstraction device layer so that device drivers from hardware vendors like Mellanox and MLX and Intel and others can plug into and provide native drivers. Again, instead of, traditionally for VMware, our partners have provided drivers ported from Linux using a shim layer called VMK Linux that VMware provides. It's a GPL component which translates from Linux drivers and Linux API calls to VMkernel internal API calls. Now that, as I just mentioned, has overheads associated with data structure translation, marshalling, unmarshalling, and incompatibilities and so on. So in order to even get the lowest latencies and get better performance, we're introducing a native VMkernel API, and we're providing a device layer for that. And this is work in progress towards future release. Okay, now switching to how the north-south traffic, how you can offer RDMA to virtual machines, guest OSs. We had talked about 6 different options last year. I'd call them option A through F at last year's workshop. They're either directly full function pass-through is directly exposing the entire PCI device to the virtual machine, and then the native device driver for the device in the guest OS has direct access, which means that you have all the MMIO or PIO accesses you make to the device. All the RDMA operations themselves are directly happening to the device. The hypervisor is not intercepting them. The hypervisor doesn't know what's going on as far as that's concerned. Now, the disadvantage of that approach is, of course, if you have only one RDMA HCA in a host, you've dedicated that for one virtual machine, and it cannot be shared by other virtual machines or by the hypervisor. So, PCI SIG has a standard called SR-IOV. It's been out for a few years, single root I/O virtualization, that lets PCI devices, PCIe devices that implement the SR-IOV spec, divide a PCI device into sub-functions. They're called virtual functions. They are sort of miniature clones of the full physical PCI function, but they give you an ability to assign these virtual functions to different virtual machines. So now suddenly your PCI device is shareable by virtual machines. But again, in that scenario, you're still using pass-through, and the driver from the vendor there's a special driver for driving to the virtual function interface, but that has direct hardware access to the virtual function. Then there were 3 soft-RoCE-based approaches we briefly talked about last year. Either soft-RoCE to a direct assigned 10 gigabit NIC, or soft-RoCE over a paravirtualized NIC like a VMXNet 3 virtual NIC that VMware offers, or in the KVM or Hyper-V environments you could use their paravirtual NICs, or you could use soft-RoCE similarly over paravirtual NICs, but between virtual machines on the same host, where you don't require an RDMA stack in the hypervisor. And finally, we propose, what we call the holy grail is, the ideal solution from our point of view, which gives the best flexibility and mobility, the ability to migrate these virtual machines and take snapshots and so on, is a new paravirtual device similar to a paravirtual NIC, but which offers RDMA capabilities to virtual machines. So the first one, full function pass-through has been available for a few years now, since the 4.0 release of ESXi, since we started calling it vSphere. Just say that again. Which building? SR-IOV pass-through was first offered in 5.1, though internally, VMware was one of the first to demonstrate the use of SR-IOV for pass-through with live migration support. We demonstrated it back in 2008, both at VMworld and at Intel's developer conference. But we don't support that anymore because it ran into, we solved the hard technical problems, but couldn't solve the political problems in dealing with the Linux kernel community and, the community at large. So, but we're working on different approaches to solving the, pass-through with vMotion support that I won't go into in this talk. But the flavor of SR-IOV support in 5.1 is still fixed pass-through in the sense that your virtual functions, once passed through to a virtual machine, the virtual machine cannot be moved to other hosts, or you cannot do snapshots and so on. And then SoftRocky, is experimental. It's not part of any upstream or distro provided OFIT stack. So we don't quite recommend that, for use in production environments. And Paravirtual RDMA is something we have been prototyping in the CTO office, and our product teams are, thinking about how to deliver it in the future release. So again, one level lower detail of what SR-IOV pass-through means is you could take any HCA which implements SR-IOV. Many adapters and vendors provide this in firmware, but because the hardware was baked before SR-IOV was standardized, but newer adapters have it natively supported at hardware level. And so the virtual functions can be directly assigned to a virtual machine, and the physical function is controlled by the hypervisor. It maintains control for many reasons, including, so that it can use it itself for, uplink traffic, for example, or for, the east-west traffic like vMotion that we talked about, but also for security reasons. So for things like, for NIC pass-through, you don't want a virtual machine to use a virtual function interface and bypass the hypervisor and do MAC address spoofing, or put a NIC in promiscuous mode and start sniffing the entire port's traffic. So you want the hypervisor to be in control of that, and it does that by controlling the physical function of the device. And then anything that the virtual function through the guest OS requests to do, like putting a NIC in promiscuous mode or overriding the MAC address, it has to consult with the physical function driver in the hypervisor saying, am I permitted to do that? And based on the privileges set by the administrator for the hypervisor, you're allowed or not allowed to do that. But it's still direct path, it's still pass-through, which means it's incompatible with a lot of the value-add features that virtualization brings, like live migration or snapshots. But it gives you the lowest latencies of the solutions. VRDMA is something I'd also mentioned briefly. Last year, I'll go into some more detail soon in a couple of minutes. But essentially, you provide a paravirtualized device interface in the guest OS. We provide a device driver to use that paravirtualized device interface. We emulate that device interface, or emulation is not quite the right term, but implement the paravirtual device in the hypervisor. And then if the traffic is going out to either a physical server or to other virtual machines hosted on other servers, we make use of the RDMA stack at the hypervisor level to essentially tie the verbs calls, things like registering a memory region in the guest OS. The buffers are directly registered in the memory region created and associated with the physical HCA, so that you get the benefits of low latency and direct DMA to the guest buffers. And interrupts are the only thing which are proxied. So when a physical completion interrupt comes in, it's still taken by, the interrupt is handled in the hypervisor, has to figure out what queue pair completed, and then raise a virtual interrupt to the appropriate virtual machine. And we consider this a holy grail because it gives us the mobility, live migration, and snapshot capabilities. Now I'm going to go into some more details about thinking about how we would implement this. In the guest kernel, we provide a VRDMA device driver, and we also have to provide a libVRDMA provider library, which understands and plumbs the verbs calls down to VRDMA device driver. So this is similar to like a libMLX4 library that Mellanox would provide, or similar libraries from QLogic or Intel. So the VRDMA device driver registers itself with the kernel core IB core driver, and it implements the mandatory verbs that are required by any RDMA provider. And it instead of marshalling and unmarshalling the verbs themselves, the IB user verbs, we decided to tunnel or reuse the user verbs as the device interface to the paravirtual device. It's a pretty efficient interface. It's a union of structures. Yeah, it can be complex because it's a union of many different structure types and enums and so on. But it's why reinvent the wheel when that serves our purpose. So in this example here, we've shown the command query device and the command query, how the query device verb is implemented in this case. The IBV query device verb is tunneled as a hypercall called command query device. Oh, I forgot to mention, we used the virtual machine communication interface, or VMCI interface, as a PCI virtual device in the virtual machine to tunnel these hypercalls over. It provides programmed I/O ports over which you do ins and outs to make the hypercalls to the hypervisor. And so we tunnel this command query device hypercall down to the hypervisor, and the hypervisor implementation responds with the response, the attributes of the device. Now going down to the VMkernel layer, this is what the backend does in response to the command query device. So what I initially call the emulation layer in the hypervisor, or the implementation of the paravirtual device, can either, if you have a physical HCA underlying, you can use the verbs provided by the RDMA stack to do the same query device to the native RDMA, so the physical RDMA driver, and cache the results of what it reports, or you can fake it. You can make up some virtual port description and report it back to the virtual machine over VMCI. Okay, for communication for the data path, first we'll talk about how this data path would work across different hosts. So in this scenario, you have an RDMA stack in the VM kernel, in the hypervisor, and you have a physical HCA. And so, as I mentioned before, we use the user verbs commands to tunnel, to make the hypercalls down over VMCI to the VMCI VRDMA endpoint in the VM kernel. And that, in turn, makes kernel verbs calls down to the RDMA stack. And so things like memory registration, you create a memory region, and you register the guest buffers, translate them into machine addresses, and create those memory regions and register them with the HCAs. And then when the post-send command is sent from the guest, you in turn send a post-send command down to the RDMA stack, and now the memory region, which was pre-registered, and the buffers, the addresses. So now the HCA knows the machine addresses where the DMAs need to happen from and to. And so when the RDMA operation happens, it doesn't care or know that this is happening to virtual machine memory versus OS memory. It just does the RDMA operation. And then on the receiver end, the buffers appear in the guest OS memory. Now, when the VMs are communicating on the same host, you don't need an RDMA stack in the hypervisor. You can essentially bypass it, and what you need to translate that RDMA post-send verb to is something as simple as a mem copy from a source to a destination buffer. And then you complete the RDMA operation. Okay, so the current status is, we started this prototype last summer, like we promised last year at the OFA workshop, that we'll be prototyping it soon. We had an intern last summer who started on this. He got quite a ways through at least implementing the management datagrams, verbs functionality. The data path is implemented, but it's not quite working, so we're going to have another internship, another intern starting soon to finish that work. And we estimate just based on back-of-the-envelope calculations based on what we know of how many VM exits you have to take, how many layers of translation we have to go through, where we have to pay the cost for interrupts, what we know about how much delivering interrupts costs, what we know about how much a VM exit costs. Our back-of-the-envelope calculation is about 5 microseconds, half round trip latencies delivered for for RDMA send verbs with polling completions.